sorry for this. So our second speaker in the morning is Hiroshige Shiga from Sangyo. That's difficult to say. So that's the type of uniform domains and generalized Cantor sets.
Thank you. Thank you very much. I'm very happy to be here with so many people. Recently, I'm working on some classical object like harmonic analysis on conformal surface and geometric function theory involving quasiconformal mappings. Today, this talk is some of my research about that. So the title said uniform domains and general Cantor sets. So I think so uniform domains comes from the notion of the geometric function theory. So I think many people are not familiar of such kind of things. So start with the definition of the uniform domains. What is that? So we consider domain D in complex plane. It is called a uniform domain. So actually, it is introduced by a paper of Martio and Sarvas in 1979. So it's sometimes it is C uniform domain for some constant C. If and only there is some C such that for any point in the domain, 2 point A, B, there exists a curve gamma which connects A and B. Such times the following two conditions. The first one is called U1. So the absolute variable gamma means length of gamma is less than or equal to C times A minus B. The absolute that is the distance between A and B. And second condition, U2, is it's a little some complicated one. For any point on the curve, Z on the curve, minimum at gamma 1 and gamma 2. So gamma 1, gamma 2 component of the gamma minus Z, and the length, so the shorter one is not less than or less than is C times distance. The point D is bounded. So the first condition means the gamma is not so long compared with the distance the point. So if you consider something like some spiral domain, right? Then it does not satisfy this condition. Okay? Because spiral domain, so if you take 2 points A and B, then so you can draw like curves like this one. Then the length of this curve is much bigger than the distance of A and B. And the second one is so here it's A at B, and so with the gamma like this, and take any point Z on gamma, and so in this picture, so here's gamma 1, gamma 2. In this picture, so the length of gamma 1 may be shorter than the length of gamma 2. So here the minimum is the length of gamma 1. So this inequality means the gamma does not pass through near the boundary, not so much, so long time. Yeah. So, for example, so a cusp domain like this is not a uniform domain because so if you take this line gamma, then distance here is much shorter than the distance here because tangents. So is the definition of the uniform domain. So it is, as I said, it is introduced by this paper 1979. After that, this domain is so useful in the theory of geometric function theory or the sort of quasiconformal mappings. So I will show you some known result, known fact. Actually, you can see such kind of theory in the book, a monograph by Gary Hart, they published in 1925 from the MS. So the first thing is, if domain is simply connected, then it is a quasi-disk if and only it is a uniform domain. And second fact is, if the domain is uniform, then there exists, so there's some constant k such that the component of the complement is either the single point or k quasi-disk. So quasi-disk, it means the image of the unit disk via the quasiconformal mapping of the whole complex plane. And so that's this. The second fact means so uniform domain is closely related to the quasiconformal mappings. And the third one is also interesting. If the domain D is finitely connected, means the complement consists of finitely many connected components. Then the converse of the second statement is true. Okay. But so. What interesting thing is for me is the case of infinite connected case. So in this talk I will talk about this. And recently, a paper of Helm shows that uniform domain is related to hyperbolic geometry. So in the paper of 2021, he shows that the domain is C uniform. Then, if and only so K is the quasi-hyperbolic distance. I'll show the definition later. Anyway, is compared with a little bit complicated distance J. Is also H is a hyperbolic distance on the domain. Between the 2 point AB is also less than 3 times this distance. The quasi-hyperbolic distance is defined by this way. So delta Z is distance of the point to the boundary of the domain. So if the domain is upper plane, then quasi-hyperbolic distance is was the same as a hyperbolic distance. So yeah. So that's the first object of my talk. And the second one is also generalized Cantor set. It is a generalization of the well-known standard one-third Cantor set. So, as you know, the standard one is first take a unit interval and divide it into three parts with the same length. So that means because the interval is length 1, then we take three intervals of length 1/3, and we take middle ones, the open interval. Then we have two closed intervals of the length 1/3, and the second step is to close interval of length 1/3. We divide them into three intervals of the same length and take middle ones, and repeat the same operation many times, and we finally get a standard Cantor set, which is closed perfect set, uncountable many, consider uncountable many points. And so, but here we can generalize these operations. Okay? First we take omega, which consists, which the sequence of the positive number is less than 1, even the sequence of the number less than 1, so Q1, Q2 dot. And for this sequence omega, we define the Cantor set denoted by E omega. How to make it? So the first step is first we start at the unit interval I, closed unit interval, and we consider J1, which is open interval in I, whose length is Q1 times the length of I. So that is just a length Q1 in this case, such that so we remove J1 with the open interval, then we have two closed interval, I11 and I12. Those are the same lengths. Okay. So if Q1 is 1/3, then it is just the first step of the standard Cantor set. And so we put E1 is union of those two intervals, and step 3 is we do the same things, but the ratio of the removed interval with Q2, Q2 times of this blue interval. So we consider the J21, which is open interval of this left blue interval, and remove this interval so that the remaining two intervals are the same length. And the same thing will take the same operation in the right interval. And we make E2, which is a union of 4 closed intervals. So we repeat such kind of operations with respect to this, the first, the sequence omega. Okay? So, so in K, in the K step, consists of 2 to the K closed intervals, different closed intervals with the same length. And step EK2 with the same operation, and EK plus 1 consists of 2 to the K plus 1 closed interval. We denote by this symbol. So this subscript means the number of steps. So, okay. And So our generalized Cantor set is E of omega is just intersection of K. Especially we said we put double zero is a sequence of 1/3, and then E omega 0 is a standard Cantor set. Okay. So we want to know. So if we take two sequence omega 1 and omega 2, we have two general Cantor sets. And complement is Riemann subs or plane domain with uncountably many boundary components. It's open Riemann subs, but somehow complicated open Riemann subs. So we like to know when those two domains or Riemann subs are quasiconformal equivalent. So we said that the two Cantor sets E omega 1 and E omega 2 are quasiconformal equivalent if there exists some quasiconformal mapping of the Riemann sphere such that the image of the E omega 1 is equal to E omega 2 via this quasiconformal mapping. And we also define the modularized space of the Cantor set or omega, which is a sequence. So we take omega in the sequence, then M omega, which is we call the modularized space of omega. It is the set of omega prime of sequence such that E omega prime and E omega are quasiconformal equivalent. Actually, we want to know for a given omega what is E omega. So I want to know the space of a sequence so that those Cantor sets that are quasiconformal equivalent. So actually we have some result about this problem, and to state our result, I'll show some special terms of the sequence. So for a given delta, which is a positive number less than 1, we said that the sequence of omega has lower bounds if every Qn is greater than delta. So that's a standard, I think standard notation. So we have some result about this. It is a paper of 2022. So let omega and omega tilde be a sequence, and also both delta lower bound for some delta. And we put some strange one. It is something like this. So we did by d omega and omega tilde. The first result is if d omega tilde is bounded finite, then those Cantor set E omega tilde is quasiconformal equivalent. And moreover, the dilation is controlled by this d omega tilde. So that is, if this is finite, then there exists a phi, which is a quasiconformal mapping of the Riemann structure itself, with the image in omega is E omega tilde, and also the maximum dilatation is exponential something like this. Well, this C delta is a constant depending on delta. And second one is if this quantity is something strange one is the limit of this log is zero bunch, then so it both quasiconformal equivalent, but especially in particularly E omega tilde is asymptotically conformal to E omega. That means if we have two Cantor set, that is E omega, and this is E omega prime. So asymptotically conformal means for any epsilon, there exists some neighborhood of E neighborhood E omegas, and also the quasiconformal mapping phi such that the maximal graduation of on this boundary is very close to conformal mapping. That means 1 plus is less than 1 plus equation. So that's the definition of the asymptotically conformality. So in particular, if this condition is satisfied, then the Hausdorff dimension of the two Cantor sets are the same. We can show that. In this, in those parts, the lower bound function, delta lower bound function is crucial one, and so one knows what happens without this lower bound conditions. That is main purpose of this talk and research. So, but by the way, so of course there are two conditions. I mean, one is the lower bound condition, and another is the upper bound condition. Okay. So concerning upper bound condition is somehow familiar with especially in hypergeometry. I'll talk about that. I'll explain about this. So lower bound is Qn tend to 0. So how about upper bound? So Qn, if Qn tends to 1 or somehow supremum of Qn is 1, so what happens? It's very familiar for us because so Qn is, so remember that Qn is related to the length of the removed interval, open interval, right? So there are some steps. We have a IM, something like this, and for the next step we remove the middle interval of length, say something like this. So this length is IN, the length of IN times QN. Right? So if QN is bigger, then the remaining two closed interval is length is very small. Right? So if QN less than 1 but big, then the length remaining interval it should be the same length. Something like this, okay? The picture like this. Yeah. So in this case, what it looks like, what this picture looks like. Okay? You have this one, okay? But you can draw this something like this. So I plus because of such kind of things. So omega I, E plus I means the first time here when the Q plus I plus K height is over the epsilon, if any. And n omega plus epsilon is defined as the supremum of this quantity. So, for example, if omega 0 is the sequence of 1/3, then if epsilon is less than 1/3, then this quantity is always 1, because the sequence of the same number of sequence 1/3. So if epsilon is less than 1 or equal to 1/3, then the next step for every I plus 1 is greater than epsilon. So every I omega 0 delta 0 is epsilon I is 1. So therefore n omega 0 epsilon is 1. The supremum is also 1. Yeah. And yes. If this is if the sequence converges to 0, so it's no 2. Sorry, it existed. The next one converge to some number, which is positive number, and infinity, then this n omega epsilon is finite for some epsilon, which is less than 2. This is also easy things. But if the sequence converges to 0, then n omega epsilon is infinity, always infinity, for any epsilon. Another thing, another example is we consider omega, which is odd number, odd QN and odd, then it is 1/3. But even numbers, QN, it is 2n, 1 over 2n. Then you see n omega epsilon is always 1 if the epsilon is 1/3, because then any so 2. So any I, so I plus 1 or I plus 2, the number is Qn is less than greater than or equal to 1/3. So this quantity is 2, but an increment of Qn is 0. That means this omega does not satisfy the lower bound condition. But this quantity is finite. Okay? I don't know this such kind of condition is ever considered in the symbolic dynamics, but if you know such kind of things, let me know. So by using this quantity, we can solve the following things. Let omega is the sequence of 0, 1 intervals, and d of omega is a complement with the general Cantor set of omega. It is a uniform domain if and only this quantity is finite for some epsilon. And actually, if the let n0 is this in omega epsilon, which is finite, then the omega is where Cn0 in epsilon is also dependent on n0 and epsilon. And by using the theorem of Lamas, Martio and Sarvas, we can show that omega contains a modular space of standard Cantor set if and only the first one is so upper bound conditions, and the second one is in omega epsilon is finite for some epsilon. So the modular space of standard one Cantor set is completely characterized with these two conditions. Also, it is once we recognize this n omega epsilon, then this statement, the corollary, is also obtained from the theorem of McManus, which is another paper of McManus. And also, in particular, this from this corollary, if we consider the measure of the standard measure, standard product measure on this product space. So M infinity is the standard product measure of this space. Then the measure of the modular space of this standard one Cantor set is 0. So we can expect, or it should be, for any omega, the measure of the modular space should be 0. But I have no idea about this statement. How much is it?
15 minutes.
15 minutes. Okay. So, so I want to show some rough idea of the proof of Mann's theorem. So first of all, recall the definition of C uniform domains. So the first one is U1 is so I said that gamma is not so much wrong. The second one is gamma cannot through near the boundary for much time. So suppose it's a sufficient. So first of all, sufficiency, the proper sufficiency. Suppose that M0 also is a long direction is finite for some epsilon, and so our purpose is for any AB and the omega we find that such curve so satisfies these two conditions. So difficult case is so Cantor said on the real line, so the complement always contains an upper and lower half plane. So difficult case is the point is one point is upper and another point is lower half plane. It is essentially the difficult case. And okay, so we consider we explain this case, and so picture is like this. So A is, we assume that A is the upper half plane and B is lower half plane, and we may assume that the height of the A and B, always the height of A is greater than or equal to the height of B. And also a real part B, so it's the closest point of the real line B infinity or either by infinity is the Cantor set. So it is an essential case. So in this case, so idea is so finding so we have to draw a path from A to B. So the path has to be a path that complement of the Cantor set. So the idea is the finding of so it's a wide gate pass through from B to the upper plane. But wide gate has to be near this B infinity because I said so the gamma has to be a bit short one, and also gamma cannot pass through near the boundary so much time. So this wide means gamma does not pass through the so small neighborhood of the boundaries, and this near means the gamma should be the somehow short length. So finding this gate is somehow essential part of my method. So it's close. It's rough ideas of trend. So B infinity is a Cantor set. So we can find the verification of the sequence of closed interval. Decreasing sequence closed interval such that the intersection is just B infinity. So it's a closed interval with the length is 10 to 0. So we find the some number k such that this ik, the length of the ik is D is this height of the B, the last, in the case, the last number is where the length of ik is greater than or equal to d. So ik plus 1 is less than d. So, so here is ik. So, and from ik we have some given some interval. Okay. So this is the last interval involving b infinity with of length this distance. So almost this picture is a square. Okay. So and because of our n epsilon omega epsilon is finite, so it is m0, then some number by definition e cube plus n0 is greater than or equal to epsilon, but another k plus 1, k plus n0 is less than epsilon. So this means length of the so the remaining, the length of the remaining interval is somehow long. But this is the distance of the removed one is also the somehow long. So we can find finally some open gate, some wide gate near or inside of the ik. So that's the very rough idea of our method. So after all, this length is compared with this height of b because of this or condition like this, and also this gate with this the gate is also compared with something about this compared with this height because of this conditions. So it's something like it is very small. It could be very small picture, but if we normalize this picture, then it's also the somehow square tiles pictures. So you can draw this green lines, which is not so much length, and also does not pass through the near the boundary so much time. And after entering the upper half plane, so A is somehow here, and after entering the upper half plane, we can connect this part and A by using the hyperbourgeoisie. Then after this curve, we can check that satisfies due to U1, U2 conditions. Then so we find curve gamma on accepting this condition of the uniform domains. So okay, so necessity is just similar ideas, but I have not much time, so I stop here.
Questions? Gavino.
So you said that so quasi-disk is the same as simply connected uniform domain, right?
Right.
So is there any connection between the dilatation of the quasidis, that is the quasiconformal map you use to define quasidis, and the constant C using the uniform definition of
Exists.
Okay.
But I don't remember.
That's enough.
Is there some cutoff where you know that a QC map in the complement of the Cantor set can be extended over the Cantor set?
Standard composite is also, yes.
It's removable.
Yeah, removable. Yeah, but in
It
general,
depends on how the dimension.
Yeah, so that's the question.
And you only consider linear canvasite, right?
yeah.
So that how the dimension actually.
No, I don't know.
Yeah, linear canvasite.
Yeah, it's okay. I don't know.
Yeah, but it just whether if it is a finite number, or you have an infinite number.
Yeah. So I don't know.
Yeah, so if it's a finite number, you can
It's
calculate
okay.
it. Yeah, but that infinite number may not be
Not
formula,
I
right?
don't know.
Yeah.
Because you use that in your corollary, didn't you? You use some sort of, because you had some reference to a paper, I think. In your corollary where you looked at the...
By the way, so in this, in this result, so we said that so first result it is quasiconformal equivalent. In this case, our quasiconformal mapping is upper half plane to the upper plane, lower half plane. So actually, we construct the quasiconformal mapping on the upper half plane and lower half plane. So this is the extent. So in other, so the first statement just shown is a component of quasiconformal mapping. There's a component of two composite that's quasiconformal equivalent. That's open linear subset. No, actually it is extendable to the whole linear subset.
Okay, more questions? So we thank Hiroshige again. Now we have time for coffee. It should be somewhere there.